Okay, so good evening, everyone. And I'd like to welcome Thomas Hesslenberg from Elliot Wood Structural Engineers. They are based down the road in Whitfield Street, which is just off Tottenham Court Road, in a very interesting setup. They've got an organisation called the Building Society, where they're based, but they're also a whole bunch of other architects and other consultants are based there too, and they have events there. So I've been to an interesting event. I know the Engineering Society also, no, the Engineering Club has events there. It's run by Andrew Scoon, so worth a look. Look out for things going down there. It's a good spot. Thomas has been teaching for a couple of years, or maybe 2 years. So in the second semester for our BA students and MArch students, sort of acting as a kind of consultant to the projects in a way. So he's seen student projects, and I hope we can persuade him back next term to do the same. It's been super interesting, and also because of Thomas's interest in this idea of decarbonising structure, or just understanding the carbon content of structure and your decisions as a designer and how they impact on that carbon content. So it's great to have you in to speak. So and you have some very nice publications that I think you have to persuade Thomas to give you at the end of the talk. But thanks very much. Thank you.
Hi everyone. Okay, I'm on the mic. So yeah, I'm from Elliot Wood. I'm going to be talking about decarbonising the structure. I'm going to still be presenting about myself, my company, Elliot Wood, the Institution of Structural Engineers Carbon Tool, which we developed with them, and how we as a sort of structural engineering practice are using that tool in our design process of learning how much embodied carbon is in our structures that we're designing, how it sort of increases the project develops, and I'll sort of talk through some examples, and then at the end I'm going to talk about 2 of the sort of most common building materials that you use in the construction industry and their carbon impacts. Happy for sort of questions at the end, but if you have any questions during, put your hand up and we can get touch on it. So here I am, a younger self of me, sort of less of a beard. I've been at Elliot Wood 6 years, came from there started there as a grad, and went to Cardiff University and did a master's in architectural engineering with a year out in Germany, where I studied architecture for a year, which was quite interesting. I'm part of my company's sustainability team and also a member of ACAN, which is the Architecture's Climate Action Network. Some of you guys might have heard of them. My sort of passion, or sort of my driver, is to push the industry away from being so carbon hungry and try and reuse more of the existing, because there's so many great buildings out there. Why not reuse what we've got when we're developing? This is my company. We are a friendly bunch of sort of engineering nerds, and the photos obviously from a couple of years ago, couldn't get that many of us together, but this is at our 25-year anniversary, which was 2 or 3 years ago, up at the Ned, which is great. And then just a little bit more, we have offices up in London, Wimbledon, Nottingham. Our overarching aim is to engineer a better society, slap bang in the middle, and we sort of have our drivers of ethics, what our values are, and a manifesto there. And just some examples of some of our projects that we've worked on and are currently working on at the moment. So you see there a Ned in the middle, the Ritz Hotel, which is starting on site soon, Grain House, which is on Drury Lane, and Berkeley Square, which is a steel and CLT building, which has been really interesting to work on, especially in the current climate with fire engineering. As a company, we've come out with our manifesto, of which I have a number of copies. We launched this in 2019, and it was introducing ethics, which stands for education, technology, healthcare, infrastructure, culture, and sustainability. Instead of looking back 25 years, we wanted to look forward and address sort of the big questions that surrounded those topics. And we appreciate it's not going to be just us that does it, it's a collaborative effort, and that's why we're posing the questions in there. And then subsequently, earlier last year, we did some research with the Grosvenor Group and came out with our circular guide or a guide to deconstructing buildings for circular reuse, where we've learned from that experience and put a 12-point plan together of how you can effectively get reuse to work for your project and what you need to do your investigations, etc. We also look there in the evaluation reuse potential of steel, timber, masonry and concrete. So diving into what I'm here to talk about, reducing the carbon impact of the construction industry, which we're aiming for carbon net zero at the moment. As we all know, time is ticking and deforestation is happening. It's happening for anyone in the built industry, it's happening for anyone outside as well. And we recognise that our planet is rapidly changing. To sort of add into that, here's some nice scary stats. Start at the top, sort of the 33.1 billion tonnes of man-made CO2 created worldwide, 40% of that is attributed to the construction industry. Demolition and excavation, debris from construction industry represents 63% of total annual UK waste, and an estimated of 80% of products' environmental impact is determined at the design stage. And what that means is just the sort of addresses the importance of why making the crucial decisions at the beginning of a project's life has so much more of a big impact rather than doing it when it's on site. As you guys are all probably aware, COP is happening at the moment, and great to see, and it's quite timely for my presentation today. And on to sort of time to do more. If we're going to positively impact society, it's sort of our individual and a collective responsibility to change the way that we use materials in the design of buildings and infrastructure. We can't do it just by ourselves, we have to work together. The construction industry itself needs to change, and it has had to for a long time, but it's such a big beast to try and change. Asking for legislative change is being asked for all the time and not happening quick enough. And what we're seeing more actually is we need to change, and for the way they operate and build, it's happening with private sector, it needs to happen across the board. A couple of years ago, the UK government announced a climate emergency. It was back in 2019. Architects Declare came about with a number of, hundreds of practices signing up. And also UK structural engineers, Declare was drawn up. To date, there's over 211 practices that have signed up, acknowledging that we are in a climate emergency and ways to get to net zero. Of that, of course, Elliot Wood is the signatory. From those Declare groups, we've got ACAN that have come about, and also LETI. If you're not aware of them, Google them, understand what they're doing. They're really helping to try and push the industry. There are groups of volunteers that have come together. Architects Climate Action Network has also got StuCan, which is for students, and it's not only for architects, it's for built environment professionals as well. And then LETI is a group of professionals that have come together and are providing guidance to the built industry, which is desperately needed. So I'll start off with something that some of you may know about, some of you may not. What is embodied carbon? It is the carbon emissions associated for the production of materials, and it's different to operational carbon, which is from the use of the building. So it comes from all the amount of energy that is used to create the materials, and then also what is associated with it at the end of its life. So here is carbon life cycle stages. We start with the product stage. Ooh, one step too far. Product stage, which is A1 to A3. This covers all emissions associated with extracting raw materials and turning them into manufactured product. Then the A4 and A5 is the construction process, which is for transport of the materials to site, and then also the construction and installation process. Life cycle stage B, which is B1 to B5, that covers in use. So as you can see there, use, maintenance, repair, replacement, and refurb. There is also B6 and B7. Then you've got end of life, when the building is ready to be demolished. There's obviously associated carbon costs with that as well, and that's covered in these four, C1 to C4. And that is your whole life carbon, which is your A to C modules. Beyond that is D, benefits of and loads beyond the system boundary, and that is anything that's associated with reuse and recycling of the materials, and that's captured as a quantitative figure for materials. Whole life carbon is life cycle stages A to C. Upfront carbon is A1 to A5. B is not typically considered by us structural engineers because we design a building for its whole building life. We don't expect to have to remove a column and replace it during its life. And then C at the end, D reported separately. And there we go. This has been put together as sort of a hierarchy of how to reduce the embodied carbon of your building. Obviously, the big step is use less stuff. And first off is build nothing. Don't do any changes to your building because you don't expend any carbon with that. Secondly, build less, build clever, build efficiently, and minimize waste. You can then ultimately specify low carbon, and you're never going to not have any embodied carbon that you can't get rid of if you're building new. So last worst case scenario is offsetting, and that should be the last resort. In response, back in August 2020, the Institution of Structural Engineers launched this guide on how to calculate embodied carbon. There are the RICS whole life carbon guide details out how sort of embodied and carbon calculations, embodied carbon and operational carbon calculations should be done. But this was the first step taken by the iStructE to help structural engineers do the assessment correctly for structures. At Elliot Wood, we've had a carbon tool since 2010, and we've sort of been developing it ourselves. We're a small, medium enterprise. And what we noticed that typically larger companies, they were developing their tools, making them fantastic, and then selling them. Well, if you wanted to use them, you sell them. What we did is we approached the iStructE following the launch of their embodied carbon tool, and we said we'd like to give our tool for free and develop with yourselves. And that's what we've done, and that's the structural carbon tool, which anyone is able to download for free. I highly recommend that you do, because you can use it on your projects, provide some sort of data in there which will be really useful, and it doesn't only just cover the standard. You can add in material database, not sort of values into there for yourself. So far it's had over sort of 2,000 plus downloads, which is great to see. It's not just about calculating carbon, it's about reducing carbon. The fact that people are using it and thinking about how they can take carbon out of their buildings is massive. If you can see that option A has 60% less carbon than option B, why wouldn't you want to go ahead with option A? It's the better choice. Structural carbon tool, here it is. This is what you're greeted with as a scheme page. I'll talk through a couple of the key features of the tool. We have here the scheme input page, and at the bottom you've got a number of tabs indicating what sheets available to you. All fairly self-explanatory when you have the welcome and the user guides to how you can use it. At the top, you put in your scheme name for what your project is, and you've got 6 scheme options that you can compare, which is really useful if you've got a number of different schemes and you use it early stages. So we've got here the scheme test 1. And then at the top left, you enter in your materials. So here we've got concrete entered, what type of material type is it? It's in situ, material spec, where it is associated within your building, description of that, which is optional, volume or a mass that you're putting in. Then you can input also a material quantity and if there's any reinforcement in the case of concrete. Then outcomes from the life cycle material data, the total embodied carbon that's associated with that element. It's A1 to A3, it's cradle to gate, it's transport, it's associated site waste, end of life C2 to C4, and then benefits outside of the system boundary. And then the bottom left here, we have then got output of all your materials and for your building, and this is the embodied carbon value that you get for your project. And that's here shown quite nicely of total tons of CO2 emissions and associated sequestered carbon, which I'll touch on in a bit. And then to the left of that, or on the right, what it is per meter squared of your building, so your floor area. The floor area is calculated as your gross internal floor area, doesn't include any external spaces such as your roof or balconies, and that's sort of defined in the project info tab. What's also available then is the graphics here to show where your embodied carbon is based or where it is in the structure. So it's split out into the different sectors. So in piling here is the biggest value. And this is a really good way of highlighting where there could be efficiencies made in your structure. So we could say, okay, there's a lot of concrete that's going into the piling. Can we reduce that anyway? Can we bring it down? You've then got project scheme releases. There's some nice fun facts, not fun, but ways of interpreting the data. You can see tons of CO2 emissions. What does that actually mean? Well, in this case, it equates to 418 average family cars running for 1 year. You can see the impact that a building can actually have in terms of carbon emissions. We then have our performance targets, and I mentioned Leti before. They have come out with their own targets, REBA and scores, and scores is set by the iStruct-E. REBA have their targets as well. And finally, the scores rating, which we've got here on the right, is a nice sort of way of demonstrating, in terms of almost like with electrical goods, where is your project based and where do we need to get to? And that is our that is the scheme page. Leading on then to the comparisons page, where you've got your number of different schemes. You can here easily compare them with like-for-like graphs. Your estimated total embodied carbon, compare that with the different schemes. Then you've also got how it is per life cycle, the scheme ratings, which automatically updates to say which is the better scheme. It just so happens that in this case, 1, 2, 3, 4 info is different. And how that compares to the 2030 targets, which are set by Leti and REBA. If you guys think it's great, which we think we do as well, which we think it is, you can download it from the iStruct-E, and it's called the Structural Carbon Tool. So, as I mentioned, we've had the tool since 2010. How have we been using it ourselves? And when do we use it? So here are our REBA life cycle stages. And as I mentioned earlier, 80% of the embodied carbon decision is right at the beginning of a project. So straight away, REBA stage 1, that's when we use the tool. It really helps the early decision making being made. Clients are sat there saying, how am I going to make a positive impact with this building? And what's the best way? And this is a really quick, easy way for us to say, this is where wins can be made if you go for a steel frame building as opposed to a concrete, and those sort of balances. Bring in timber as well. Then again, once we've narrowed down a couple of the options, we'll use it at REBA stage 2. Unsurprising, use it at REBA stage 3, and then again at REBA stage 4. And in that process, we can see how the embodied carbon value changes for our structures or for our buildings, because we're getting into more details. We get down the REBA stages, and you can see it slowly increases in most cases with our projects. And that's not unsurprising because finer details are coming together and so on. That's when typically we would stop with using the tool because the project's handed over onto site for construction. What we'd love to see is for more contractors to use the tool to then actually say, okay, real life, this is how much we're putting in. We can say what everything should be sized at, and the contractor follows that, but they will sometimes make some other decisions of say, we've dug a little bit too big here, we'll put some extra concrete in. That needs to get captured in some way. So here's a project example of one that was done at stage 2. We looked at 5 different frame options for the Hive building. And this was a really nice way to explain to the client if we went for a steel RC mail deck frame, precast RC frame with 50% GGBS, 70% GGBS, or if it was steel with a CLT panelized system. And there's carbon savings as you go around. So unsurprising really that the steel and RC mail deck frame is the worst option because you're combining 2 of the most polluting materials together, and flip round to this panelized CLT when we're storing carbon. That's the better option. Here's an example of a building that we've got around the corner from us. It's the network building. Stage 1, we ran the tool through with the steel and CLT frame and another frame option, had its values. And then at stage 2, once we developed the design, we ran it through the tool again. And there we saw an increase of about 382 tons of CO2 emissions. This is something that we've used recently on a number of projects, and it's a really good way of, this is called the waterfall diagram, and it's a good way of explaining how can we make embodied carbon savings in your project once a scheme has been staged. So at the top, at the beginning, this is baseline. If it's a 12 by 12 grid, flat slab. If we reduce that structural grid, we actually see a carbon saving drop off a couple of points. Raise the basement, drop a couple more points. Then we find ourselves at the baseline planning scheme. Do some extra steps, bring down that value, bring it below the lessee target, and just by those small little tweaks, we can get down to the developed design target, which is a great value that we found there. Then you look at some other options which could be adopted. It's not just about one big idea, it's about the little ideas and how they accumulate, and that's how this diagram's sort of been set up, so you can see those benefits. What we've also found from using the tool is how much of an impact basements have. And from the projects that we've got in-house in the company, we've only found that one of our basement projects hits a lessee target. All the others are above. And it's unsurprising because to do a basement project, you are using piled walls, concrete slabs, concrete liner walls, and that's a sort of a massive problem with that because there isn't any other material out there apart from possibly sheet pile walls, but they're also not great to create your basement. So how can you make a basement greener? Try and make your basement footprint as small as possible, or try and remove the need for it completely. Interestingly, we're looking at the moment into a little bit of study of bike storage in buildings is trying to make your company's footprint greener because everyone's going to cycle into the office. But what happens as subsequent is the bikes get stored in the basement. But you're putting so much carbon into creating a basement, that just seems ridiculous. So could you think about putting the basement elsewhere? And then as I touched on, sheet piles could be used. It's not necessarily easier to use, but the reuse potential is higher. Once your building's over and you're demoing, why not take the sheet piles out and reuse them elsewhere? Here is the way that we've been sort of tracking our projects. We've created the embodied carbon leaderboard. Over there, we've got sort of, it's on the next slide, how many projects we've got on there. But it's a really fun way of getting teams and engineers to have a bit of friendly competition inside the company to say, hey, you know, they've done a commercial building at CLT glulam, and they got 0.15 tons of CO2 emissions per metre squared. We can better that, and this is how, and they want to get higher up on the leaderboard. And there's been so many fun discussions of just people competing about it and really running to get those targets down on their own buildings. After a year of it, we had sort of a summary talk, and on there we had over sort of 27 projects that were new builds, 7 that were refurbs. On there we've included all the different types of schemes that they had, scheme types. 17 of the 60 new build projects hit LETI 2030 targets, which kind of demonstrates how difficult it is to get down to the 2030 targets. And we've got our retrofit projects, all 10 that are on there have hit the LETI target, but that's a little bit unsurprising because to calculate a refurbishment project for its embodied carbon, you use the whole building's internal floor area, not just the extension that you're adding on, the floors that you're adding on. There we go. Interestingly, embodied carbon isn't the only way that, or the best way of calculating if a building is quite green. We've got here an example of 2 buildings, one Metrobank Cardiff on Queen Street. The superstructure is steel frame with RC composite metal deck. That means that the metal deck slab is physically connected to the steel structure, basically entailing it's really time consuming to reuse the steel work. So its reuse potential is not that great. So its embodied carbon score was within LETI targets. It's great, fantastic. But is it easily demountable? No. Whereas we look at network building, which is a steel frame with CLT slab, that didn't hit the LETI target. It's partially down to it had a basement, but it's demountable sort of, or it's easier to demount it at the end of its life, and that's reflected in the D value. So I'm going to focus now on 2 of the materials. The first one's concrete, which everyone sort of should be familiar about it, what it is, but some sort of stats that come with it. Cement production is one of the biggest polluters, and there's a stat that's sort of bounded around that its carbon emissions mean that it's sort of the 5th worst RC emitter of countries, if it was compared to as a country. But interestingly, on our leaderboard, 5 of the top 20 are fully RC frames. And the reason for that is cement replacements are used, such as GGBS or PFA, which stands for ground granulated blast slag, and pulverized fly ash. And I'll touch on them in a second. Concrete has got roughly 96% less embodied carbon emissions than steel structure sections. That's the EU average comparison, and that's between cradle to gate, A1 to A3 stages. It's got roughly about 70% less carbon emissions than steel structural sections in its end of life. Both of those are sort of comparing weight over volume. And then finally, when you use concrete in a structure, its floor to depth ratio is very favorable, especially in high-rise structures, because you can get a nice clean flat slab and there's then no downstairs or anything. That's much more appealing to a client if they've got a high-rise and they want to maximize the floor to ceiling ratio, and it's so on and so forth. And we've done this sort of study as well, looking at the numbers behind the savings. If we look at a cube of C32 40 strength concrete, which is, I know sort of goes over the heads a little bit, but that's the most commonly used some concrete that we use in the industry. You add 25% GGBS, you see a 13% carbon saving. You add 70%, you're seeing a 54% carbon saving. So why aren't we putting more GGBS in? And PFA, it's fantastic, it's saving us carbon. Well, think again. In 2015, there was a study done to look at the potential market supply there's roughly 295 to 300 megatons of GGBS out there, and worldwide that would only meet 17% of global cement supply. So it's all well and good using the stuff, but by you using it instead of someone else, it means that another project can't even think about using GGBS. Then where does GGBS and PFA come from? Actually comes from steel production of blast oxygen furnaces. That's for GGBS. And PFA comes from the coal industry. So both of those are really bad carbon emitters. And you just think, okay, you're saving carbon from one side for your product, but there's had to be quite a lot of carbon emissions that's been associated with it in the first place. So it's not the saving grace that we wish that it was. There are other ways of saving or reducing carbon emissions in concrete. There's looking at pumping CO2 into them, and that helps it reduce a little bit, but it makes the cement harder to work with. There's also other university studies that are happening with projects up in Manchester where they're looking at using carbon fibre in your concrete to make it stronger. But again, there's so much concrete used in the industry, and this is such a small thing to think of at the moment that exploding it up to the market requirements is such a massive challenge. So there's still a long way to go with cement, and the best way of actually helping or reducing the amount of embodied carbon associated with it is just to use less of it. And an alternative material to look at then is timber, of course. Lovely picture here of someone enjoying a full timber space, glulam and CLT slabs. If we were to look at embodied carbon sequestration, that is the amount of carbon that is drawn out of the atmosphere when the tree is growing. So straight away, if we did a comparison of RC frame, steel and CLT, and glulam and CLT, you can see that number coming down, and that is down to all the amount of carbon that is stored in the timber when you use it. And if we look at it a bit more detail and look at A to C, there is actually not so much of a benefit to use it. And that is down to how we use or consider the use of timber in embodied carbon assessments. When your building's end of life is at the end of its life, those carbon savings that you've had are lost. They're given on to the next project. So suddenly you see this little jump, and that makes it a bit easier to compare to other projects when it comes to A to C. But that's not the it's not end of all. The objective at the moment is to save carbon now, and by using that CLT, using timber as a structural material, you're going to have those carbon savings now because more trees are going to have to be planted. They're going to take more out of the atmosphere. How carbon is considered, I'll sort of jump over this slide a little bit and go to this one, which shows that at the beginning of its life, all that carbon is saved already. And as I said, at the end of its life, after 60 years, which is a typical building life cycle, it's released back up into the atmosphere. But comparing that to another project that is not CLT driven, you can see that there's sort of a just above the line using carbon emissions the whole length. And you can see there's obvious benefit savings by going towards use of timber. Just noting that trees will sequester, they won't sequester that much carbon over the first 10 years of its life. But then suddenly when you get to its maximum sequestration period, which is between 10 to 50 years, that's when it's time to chop down the tree and use it as a building material, because then, you know, you can plant your next one, get more carbon savings, because you're not going to see much benefit over the rest of its life. Overall though, to finish off, it's still better, at least for the climate, to build nothing at all. And that's how I'm going to finish this one off. Thank you. Any questions?
Any questions? I have a microphone here for the people of the audience online.
Yeah, thank you, Thomas. That's great. I mean, the concrete basement problem, could you not reasonably not offset, but if you, like concrete piling, like there's Skanska, to make a thing called energy piles, where you use the piling or the foundation for the building for a ground, as a part of a ground source heat pump. So if you started to think about it doing a different job for you as well as being a basement, I think the bike storage thing's funny because it's, yeah, as you say, it's very expensive in terms of carbon. But could you not think about that? And then also the other thing, the steel thing surprises me because, yes, incredibly carbon intensive to make, but Liberty Steel, I mean, I know they've got some other problems, but all their steel it's not blast furnace. It's an electric furnace. It's remelted down. You keep remaking sections. So in a way, it's endlessly recyclable. But is it still too
We'll start with the concrete basements and the piling. There is an obvious benefit that you say, okay, if piling is the only solution for the foundations, then why not try and make it greener by having some other benefit that comes with it, if it's going to reduce the operational energy of that building. But at the same time, there's still cement that needs to go in there. And there's other solutions of maximize the GGBS content in there, because foundations, they take a little bit longer to cure. Don't go on ball sort of on the scientific side of it, but there's benefits there. But as I touched on, there isn't that much GGBS out there. So there are those benefits, but you're not solving the overall problem. You could still have ground source heat pumps and no piles. Then touching onto the steel, in the UK, we don't have any electric arc furnaces. We only have blast oxygen furnaces, and the byproduct from that is GGBS. From electric arc furnaces, the GGBS content is less. It's there, but it's not as much. And those reactors are based over in France or in Europe, mainland Europe. And yeah, there's a high embodied carbon that comes with it. But I guess the flip side, or comparing concrete with steel, steel's got a higher reuse potential. Once a building is built with steel, you can remove that section carefully, then reuse that piece of steelwork as long as you do the necessary testing. Whereas with concrete, as soon as that's come to the end of its life, it's crushed, it's broken down into aggregates, and it's reused elsewhere. But it's not reused, it's downcycled as a material. Whereas at least with steel, it can be direct reuse for reuse, which is fantastic. In our circular reuse guide, we asked demolition contractors, who usually come onto a project REBA stage 4 when the project's about to start to go onto site. And when they come on, they love to their contract is demolished straight away. And they'll take it off, and those steelwork won't get reconsidered for reuse. It'll just get melted down and turned into new sections or into new materials. And when asked sort of why don't you unbolt a beam instead of just cutting it, they've never been asked, their response was, we've never been asked to do that. So it's not in their prerogative. So the attitude of the industry needs to change, that you say, come on board earlier, here's how you guys can help us and try and create a reuse market, which is seriously lacking in the industry at the moment. But it's happening slowly.
Thanks very much.
Anyways. Yeah.
In a situation like that, could you just predict that those demolition contractors will be out of work by the time the building comes to the end of its life cycle? If you created the building to be completely dismountable for robotics, is that a good solution?
Are you suggesting, could you rephrase that? Rephrase the question? Or
do you even need to have these conversations with demolition contractors? Do you think that they will still be in those roles by the time the building comes to the end of its life cycle?
yeah, I think they need to adapt and they need to change their way of thinking.
If they can't adapt, what happens?
In case of sort of robots taking down buildings.
In evolution.
I can't envisage where they can't be still available, sort of useful to help demolish a building, but not to the same extent. We're always going to need new buildings. So their purpose or their needs always going to be prevalent. It's just how are they used better and how do they adapt to be able to help the marketplace. And I guess you can be really crude and sort of say survive or die.
Do you think we should just completely change the market?
Yes, it needs to happen. Because at the moment, we're not going to, business as usual case is not going to help us as a planet. We're going to stick with those horrible stats I said at the beginning. We need to get down to net zero, and the only way to do that is by adapting. And there will be a big shift in the industry. Just it's such a sort of massive monster. How it's going to change is going to be really tricky.
I understand like why the current system is a monster, like as you've said it. Do you think that, like, how can we just completely change the system then? It's not working. Like, I think we can all see that. In an ideal, like, what would you suggest?
What would I suggest to helping it change? It will have to be from, and it's really painful sort of relying on it, but it's the legislative changes, the government coming in and forcing the change to happen, and that's been asked for a lot. The Architects Journals had their retrofit program, or sort of retrofit dialogue for a long time, and that's them trying to make retrofit VAT 0%, which it is for new builds, and that change isn't happening because the government doesn't see where benefit lies elsewhere. At the moment it's working for them because everyone's building new and retrofit's not as desirable, so that's sort of a way that it needs to go, is top at the change. But there is change happening within other practices, within the views of the workers and the people, and that will eventually turn to actually let's go for reuse.
Hi there. Thank you for your presentation. It was very informative. I just want to touch on timber in general, and you mentioned fire testing, fire engineering and things like that. Do you foresee a shift in the perception of timber going forward following COP26 and things like that? I know the government haven't released any information yet, but do you foresee timber becoming more of a prominent material off the back of embodied carbon and us moving forward more so in a residential sense? I know the legislation that come out with Grenfell and the reaction that was of that and everything that's come off the back of that and the arguments that happen in the background, but do you think there is a place for timber within residential high-rise construction going forward? Do we have to go down that route to achieve our net zero targets?
If we're looking at materials, building materials as they are now, and what is available to mass market, then timber is a ready-phased material to use. Glulam, CLT, and a number of other sort of engineered timber products allows for larger scale buildings to be built safely and within codes for use. And there's other benefits that come with using timber. It's a lightweight material, it means less foundations, it means a greener environment. There's the biophilic side of things as well. And so, Yes, and its biggest challenge at the moment is fire safety. Wood burns, we know that, and it's how we overcome that with the right assessments and the right attitude as well. The UK took a massive leap through Grenfell of how wood is perceived as a building material. It went straight onto the defensive, and that is something that's been fantastic with one of the projects, Berkeley Square, because that is one of the first projects that we've got timber in there. So that's great to see. There just needs to be more happening, and like with many things, the more it gets discussed, the more it gets thought through, and more people get their thinking caps on, then the more likely that it's going to become more popular or more readily used in construction. Europe is paving the way. They're really showing us how it can be done, and we just need to learn from them, but also do it in our own way so that we feel comfortable with it. European forests are what we rely on, and deforestation in Europe is at 50%, meaning that more wood is, or more timber is grown than is deforested. So currently there is so much available to us, and we know how to responsibly grow timber and grow forests, that we can continue to use that source because there is so much surplus out there. It's just having the means to use it properly, I guess is the best way of describing it. But yeah.
Thank you.
No worries.
Hi, Tom. Yeah, we've just got a couple of questions from Scott. A question from Scott and a question from Pete, texted through to me. Question from Scott. You've spoken about structure. What proportion of a building's embodied carbon does this roughly represent relative to, say, cladding, finishes, etc.? Is that sort of broken down in your the carbon
yes,
tool? Or?
It is broken down, and it's gone completely over my head, and I can't remember the exact figures, but I want to say that obviously it's dependent on the building typology and which construction, if it's residential, commercial and such. And I'm going to have to point you in the direction, Scott, of Letty and their embodied carbon guide, in which they highlight the percentage difference between a building and where its embodied carbon lies. Obviously, for a structure, that is where the majority of the embodied carbon lies within it, because for a building, that's where most of the embodied carbon goes in. It's in the structure. And that's sort of the best I can give Scott. No,
I suppose I'm just imagining if you started to think about if you were making a structure where the cladding is the structure, let's say the skin is the structure, or so then how do you use the? I suppose it's like any tool. I suppose you just have to take it. It's still about meat. It's still about mass. It's about.
Yeah. It's a really. We're doing a lot of projects at the moment where the structure is getting governed by the facade's deflection limits, or how it can, how much the beams can deflect before it becomes a problem for the cladding, and then we have our deflection limits that come with that, and that makes our beam sizes, our column sizes greater, because we can't allow them to deflect as much. And so there's a real almost sort of push and pull of who gets the benefit out from that. Should the cladding change because it's too onerous in its limitations, or does the structure just have to suck it up and be stiffer so that it can hold the cladding?
I mean, that's a more general question about engineering, isn't it?
Yeah.
I mean, also, you look at the engineering of a small extension to a house in London or something, and the foundations are can be quite large sometimes, whereas the foundations of the existing building you're attaching it to are practically non-existent. So that there's that room, there's still that scope for efficiency sort of future. Look, Pete has a question here, so I'm just going to read this out. And also just to make, just to refer back to your question about the CLT, there's a guy called John Spittle who works for VHAG, who's a big CLT supplier, whatever, and they're doing a massive project in the US at the moment, I think in Denver or something. So it's a 25-story residential tower. I think it's been built. It's on a concrete podium, so like a fireproof bit, if you like. And whatever, that's satisfied their... It's interesting. I mean, it's not
There's also a high-rise tower in Canada.
Yeah.
I think it's the tallest out of timber.
I mean, it's like you don't want to ignore obviously the Grenfell thing in terms of, but it's sort of, it's how, we've got to think about it, the reality. Anyway, Pete says, thank you for a fantastically informative lecture. Regarding timber, surely it has to be considered within the context that it is the only renewable construction material. I don't know how you calculate that value. I mean, the idea that it's grown.
That's through the sequestration of carbon, and I touched on earlier, and that's where you can calculate how much carbon is drawn out from the atmosphere over the tree's lifetime. There are only a number of different trees that we use for engineered timber products that there are codes and standards for, but like I touched on, that carbon saving you have for your building unfortunately gets passed on to the next building if you reuse it. And so that's where you saw that jump back along that graph here. But then the next building that comes along, that will see the carbon saving straight away. But then we have to just be sort of in safe hands of knowing that where your tree has been taken down, a new tree will be planted in its place, and that will store carbon in its time, and then will get cut down hopefully for another building product, and it is a renewable source. So there we go.
Well, thank you very much. Thanks for a great talk. Thank you. That's brilliant.
Cheers. If anyone's interested, I have extra copies of our Full Circle to Reuse guide, if you guys want to read that, or our manifesto as well. Yep.